Okay, so today we are going to start with Unit 3, that is frequency domain in images. Okay, so in this unit, we are going to learn all these topics. Basically, what is meaning of enhancement in frequency domain, how we can perform enhancement in frequency domain by using filtering techniques in frequency domain. And in addition to these techniques, we will be studying various transforms as mentioned here, like DFT, DCT, Hart transform, Walsh transform, and tail transform, and discrete wavelet transform. And we will be studying one more topic under image filtering, that is homomorphic filtering. Okay, so let us start with this new unit. Okay, so basically, before going for image enhancement in frequency domain, let us first understand what do you mean by frequency with respect to images. Now, whenever we consider a signal like say voltage signal or amplitude signal, it is actually one dimensional signal, or there is only one independent variable and other axis that represents amplitude of the signal. So when we plot it as a signal, it becomes two-dimensional in nature. Okay, so for this two-dimensional nature signal, we have one of the axis as time axis, and second axis is amplitude axis. And when we transform this signal to frequency domain, we get corresponding to time axis, we get one frequency axis, and again similar to amplitude, we have amplitude axis to represent amplitude of all frequency coefficients. So for a signal which is 2D in nature, 2D in the sense that there is one dependent variable and one independent variable. So independent variable is time and dependent variable is amplitude. So for signal like electric signal, we have time to frequency domain conversion, right? So now in case of images, we can say image has 3D nature when it is plotted, because it has two coordinate axes, x coordinate, y coordinate, and we have third dimension which represents intensity of pixels. So in this sense, we are calling image as having 3D nature. Okay, so when we have a signal like image, we have image space. Okay, and this image space is converted to frequency in case of images. Okay, so this is difference as compared to time. In case of electric signals, we convert time to frequency, and in case of signals like images, we convert image plane or image space to frequency domain, and hence we call it as spatial to frequency domain conversion. Okay, now what is meaning of spatial frequency or frequencies in case of images? So we can define this spatial frequency. It is actually used to describe the rate of change of pixel intensity of an image in space, and it can be visualized using the line profile or column profile of the image in any row or column. Okay, so basically spatial frequency is rate of change of pixel intensity values. So how we define frequency in time domain? We give it as 1 upon time period, right? And frequency is nothing but how many number of cycles are present in unit time, right? So it is basically rate of change of amplitude with respect to time. This is definition of frequency for a signal like electrical signal. And for signal like image, we have concept of spatial frequency. So it basically gives you rate of change of pixel intensity values with respect to unit distance, okay, or with respect to image space. Okay? So here is one example it's shown. Say this is your input image. Okay. Now we can, if you look at the image here, intensity of pixels is varying in sinusoidal fashion. And it is clear if we plot profile of one particular row from the image. So if we consider any one row of this image, profile will look like as shown here. Okay. So here, if you observe, there are some bright intensity values, then it is slowly increasing, it becomes complete white, and again it starts reducing intensity level, and here it becomes dark, very dark shades. Again, the same pattern is repeated over one particular row. So the same thing is shown here. Okay, initially it starts with some brightness value. It goes on increasing, then it goes on reducing, and for certain pixels, it becomes completely dark. Okay, so if you plot profile of any one row of this image, it looks as shown here. Okay, and with this frequency concept for images will be more clear to you. So here your pixel value or intensity of pixels is varying in a sinusoidal fashion. Okay. So this is frequency for the given image. Okay. Uh, Ma'am, there is one question. Can you show the previous slide again? Okay, so Sai, do you want this slide, spatial frequency? So this spatial frequencies actually it describes rate of change of pixel values along image space, and it will be more clear with this figure. So here intensity values are varying in a sinusoidal fashion, and we can get an idea about frequencies by either using row profiles or column profiles. Now let us have a look at few additional examples to understand concept of frequency. Okay. So if you look at these first two images, here for very first image, all pixel values are having brightest gray value, that is white. So all pixels are having value 255. If you look at second image here, all pixels are having value 0. So it is looking as complete black. Okay. Now, if we talk about frequency contents for these two images, we can say that these two images have 0 frequency value because entire all these pixels are having same value. So it is as if a DC signal. If you compare it with your electrical signal, if you have a signal with constant amplitude, we call it as DC signal. Or frequency contents for a constant amplitude signal, electrical signal. Its frequency contents are 0. Whenever you have same amplitude, frequency content is 0. It has only 0 frequency coefficient, and all other frequency coefficients take 0 value because there is no transition from one intensity value to other intensity value, and that's why these two images have only 0 frequency component. Okay, similarly, if you have one more image where all pixels are having some intermediate gray value, say 200, even that image has 0 frequency contents. Frequency, it has only 0 frequency. Okay. So these are two images with 0 frequency. Now, if you look at this third image, okay. Now, as you move along columns, you can observe that there is slow variation in intensity value. Here it is comparatively dark shades or less low bright value is present. And as you move from left to right, brightness is slowly increasing along the columns. Okay. So this is an example of image which has some low frequency component. Okay. Similarly, if you look at this image, as you move from first row to last row, slowly intensity value is increasing. So this image also has some low frequency components. Okay. Now again come to this first image, this third image. Okay. Left side image from second row. Now if you talk about only for the first column, if you consider simply first column, are there any frequency contents in first column? If you simply consider first column, you can observe that all the pixels from first column, they have same value. So if we simply talk about frequency variation along rows for the first column, frequency content is 0, because there is no variation along the rows for this very first column, and this is true for all other columns in this particular image. If you consider variation along rows, there is no variation along rows. Along rows, pixel values are remaining same, or pixel values are having constant intensity value. So along the rows, there is no variation. So for this image, we can say along the rows, frequency component is 0, but along the columns, there is low frequency. There exists low frequencies. Okay. And if you consider this last image, now if you, for this last image, if you consider variation along rows, yes, there it has low frequency component. But if you consider intensity variation along column, so again consider only very first row. For all the pixels in first row have same gray value, so there is no variation along columns. Okay. So along columns, frequency component is 0. Similarly, if you look at the last row, for last row, all the pixels are having value 255. Okay. So there is a frequency component is 0 along all columns. Okay. There is no variation along the columns. But if you are considering variation along rows, this intensity value is slowly varying. So these are examples of low frequency content in an image. Now let us move to one more example. Now, if you look at these images, here there are frequency variation. There is lots of variation in pixel intensity values. Here initially you have this transition from bright to dark. Again there is abrupt transition to bright. Again it is varying to other gray shades. Again gray shades are becoming brighter then darker. So there are multiple transitions in intensity values. Similarly, for this image, if you look at variations along rows, there are multiple transitions in intensity values. So we can say that these two images are examples of high frequency content. Okay. And if you go for natural images, in addition to horizontal variations, diagonal variations, you can also, in addition to horizontal and vertical variations, you can also have intensity variations in all other directions, diagonal directions. So there can be intensity variation in along any direction from 0 degree to 360 degree. Okay. So these are examples of high frequency contents. If you consider this complete slide as an image, here there are diagonal lines, right? So all these are frequency details in an image, and this complete slide is also an example of high frequency image, because there are these various transition along with these slant lines on the background. There is one more horizontal line. Some text is written here. Okay, so this is an example of high frequencies present in the image. Okay, so hope with these pictures you are getting concept of frequency with respect to images. So according to the data spatial distribution of gray levels in the image, you can have either low frequency contents in the image, or you can have mid frequency contents, or you can have very high frequency contents in the image. Okay. So when we transform the image from image plane or image space to Fourier domain or frequency domain, it it takes corresponding to x coordinate and y coordinate. It has frequency axis, say named as u and v. Okay, so when we consider frequency domain representation of signals like electrical signals, okay, for electrical signals, one of the axis is time, another axis is amplitude. And when we take its Fourier transform by using Fourier transform, we can transform this signal from time domain to frequency domain. And for Fourier transform, you have one axis as frequency axis and another axis is HU, which represents amplitude of these frequency coefficients. Okay, so you have one axis that is frequency axis and another axis is amplitude of frequency coefficient. So like this representation of electrical signals in frequency domain, we can have similar representation for frequency domain of images. And as this is 2D graph, we will, for images, we will get 3D graph. Okay, so just look at this picture as shown here. When we transform the image to Fourier domain, we will get one frequency axis, which is named here as W1. Then we will have another frequency axis named as W2. And this third dimension represents amplitude values of these frequency coefficients denoted by W1, W2. Like in image plane, we have X coordinate value, Y coordinate value denoted by XY, and every pixel at that particular coordinate has some intensity value, which is third dimension. Like your spatial representation, your frequency domain representation is as shown here. It has coordinate value W1, W2, and value, every frequency coefficient has some value. Okay, like images, we can also represent it in matrix form, and when we represent it in matrix form, it has two-dimensional nature. Okay, so you will have W1, W2, and value of every frequency coefficient. Okay, now why to transform images to frequency domain? Basically, whenever we want to enhance the image as per the frequency contents, this frequency domain is very useful. Say if we want to highlight simply high frequency contents in an image, then we can transform the image from image space to Fourier domain or frequency domain, and then we can select simply high frequency band or high frequency coefficients from the transformed image. Okay, and we can attenuate all remaining coefficients. Okay, so sometimes for certain applications this frequency domain works better in order to enhance the image. So this frequency domain of images is useful for image enhancement in frequency domain. It is also useful for restoration of images in frequency domain. It is also useful for compression, like this discrete cosine transform is very useful for compressing the images using frequency domain image compression techniques. Then it is also useful for segmentation and description. Okay. So as these are this frequency domain is useful for these various applications, we need to transform the image from spatial domain to frequency domain. One example of restoration using frequency domain is, say we want to design a notch filter. Okay, are you familiar with notch filter? You might have studied notch filter in DSP. What is notch filter? Notch filter basically attenuates signal of particular frequency. Okay, so this designing notch filter becomes very easy in frequency domain. Okay, so we can transform the image to frequency domain, then we can attenuate that particular frequency, and then we can after filtering we can again transform the image from transform domain back to image plane, and then we can display the image. So if we are having an image which is corrupted by particular frequency noise, we can easily do it in frequency domain by using restoration techniques in frequency domain. Okay, so this is that is why we need frequency domain of images. Okay, now let us see how we can transform the images. Okay, so basically we can consider, say, an image fxy of size m by n. Then we can take forward transform of the image by using this equation. Okay, so here fxy is your image and gxyuv represents forward transformation kernel. And by applying this forward transformation kernel on the input image fxy, we get forward transform or transform of the image represented here by capital FUV. Okay, so this we can obtain transform of the image FUV by summation 0 to m minus 1 summation 0 to n minus 1 of fxy into g of xyuv. Okay, so if your input image size is m by n, also transform image size is same as m by n. Okay, so always your transformed image f capital FUV, it has same size as your original image fxy. Okay, and this gxyuv is known as forward transformation kernel. Okay, now like forward transform, we can also apply inverse transform on the image or image transform FUV. FUV is transform of the image, and we can apply inverse transformation kernel HXYUV to reconstruct the original image FXY. Okay, so we can obtain original image fxy by this inverse transformation summation 0 to m minus 1 summation 0 to n minus 1 FUV into h of xyuv, and this hxyuv is known as inverse transformation kernel. Here m and n represent size of image. Okay, we have considered fxy, that is original image of size m by n, number of rows and columns in the given image. Okay, so FUV also has the same size, that is m by n, and when we apply inverse transform on FUV, we get original image fxy with size m by n. Okay, now just compare this transform equation for discrete Fourier transform. Do you remember equation of discrete Fourier transform? Do you remember? Can anybody type Fourier transform equation in chat box? Okay, so if you have a signal fx, consider one-dimensional signal because you are familiar with one-dimensional signal. How you can determine fu or say fw, which is Fourier transform of signal fx, discrete Fourier transform. We are talking about discrete Fourier transform. So you can determine fw by summation of fx, and this signal fx is multiplied by a term e raised to minus j 2 pi w divided by 2n, right? This is equation of Fourier transform for one-dimensional signal like electrical signal. And here this index of summation, this w varies from 0 to n minus 1. Okay. Sorry, here you should write x. X varies from 0 to n minus 1 because your vector x, it can have multiple number of samples, 1, 2, 3, 4, and so on. Accordingly, length of this vector fx is decided. Okay, so you have to consider all these samples from the given signal, multiply each term by e raised to minus j 2 pi w by 2n, and say if there are 4 samples in the input signal, this summation will vary from 0 to 3, and like this w also varies from 0 to 3. So corresponding to 4 input samples, you will get 4 frequency coefficients, F0, then F1, then F2 and F3. Okay. So corresponding to 4 input samples, you will get 4 frequency coefficients, F0, F1, F2 and F3. So W varies from 0 to 3 if we consider N as 4. Okay. So this is your Fourier transform in one-dimensional, and this term e raised to minus j 2 pi w by 2n, this is nothing but your forward transformation kernel. Okay, forward transformation kernel. Okay, so this term e raised to minus j 2 pi w by 2n represents forward transformation kernel for one-dimensional transform. Okay. Now, similarly, for two-dimensional transform, here see, for one-dimensional transform, this forward transformation kernel has two terms. That is, it has to be e raised to minus j 2 pi w into x. One more term is there, w into x. Okay, e raised to minus j 2 pi w into x. So we can call this as forward transformation kernel g, or which is function of w and x. Okay, so this is your forward transformation kernel's general representation, g of w comma x, because it is function of both, that is your x and w. Okay, sorry. Let me erase these things so that it won't interrupt next slides. Okay. So same concept is written here. This is discrete Fourier transform equation for one-dimensional signal. So your signal fx varies from x0 to w minus 1, and equivalent you can determine its Fourier transform fk, where k varies from 0 to w minus 1. Okay, so here notation w is used to represent total number of samples, x is your time domain axis, and k is notation used to represent frequency axis. Okay, so k is index for frequency coefficient, x is index for your time domain samples. Okay, so you can determine forward transform fk as summation x runs from 0 to w minus 1 f of x e raised to minus j 2 pi kx by w, and this term e raised to minus j2 pi kx by w is nothing but forward transformation kernel g x comma k. Okay, now like forward transformation we have inverse transformation. We can reconstruct original signal fx by inverse of fk, and this inverse transform is as shown here. 1 upon w summation k runs from 0 to w minus 1 f of k into e raised to j 2 pi kx by w. Okay, so here only sign of this term is changed for inverse transformation. So for Fourier transform, this e raised to j 2 pi kx by w, it represents inverse transformation kernel, that is h of k comma x. Okay, so this is concept of forward transformation kernel and inverse transformation kernel, and same concept we can extend for two-dimensional transforms. Okay, so for two dimensions, instead of simply gxu, now we have gxyuv, because for two-dimensional signal like image, we have one x coordinate and y coordinate, and when we transform it, we get corresponding to x we get u, and corresponding to y we get v. So this forward transformation kernel gxyuv for two dimensional discrete Fourier transform is as shown here. 1 upon m into n e raised to minus j2 pi ux by m plus vy by m, where m and n represents image size or matrix size. Okay, so this is forward transformation kernel for two-dimensional Fourier transform. Okay, so in one dimension we will be having we were having only one term e raised to minus j2 pi kx by w. Now, instead of one term, here we have similar two terms, e raised to minus j2 pi ux by m, okay, and another term corresponding to y, which is vy by m. And like forward transformation kernel, this is equation for inverse transformation kernel of inverse discrete Fourier transform. So this hxyuv is given by e raised to j2 pi ux by capital M plus vy by n. Okay, so this is your inverse transformation kernel for 2D DFT. Okay, now let us talk about two important properties of this forward transformation kernel or inverse transformation kernel for two-dimensional transforms. Okay, so consider forward transformation kernel G. It is said to be separable if we can separate gxyuv into two components, g1xu and g2vy. Okay, so this is known as separability. If we can separate gxyuv into one component of xu and another component of vy, we can call that this forward transformation kernel is separable. Okay, so this is known as separability property. And another property, that is symmetricity. Now, if this functionality G1XU is same as functionality G2VY, we can say that transform is separable as well as symmetric. Okay. So this is symmetry property of two-dimensional transforms. Okay. So when we can separate it into two components, it is known as separability property. And when the functionality of these two components is identical, we call it as symmetry property. Okay. So now looking at this forward transformation kernel for two-dimensional transform, tell me whether this transformation kernel GXYUV is separable. Please type your answer. Say this is two-dimensional forward transformation kernel for discrete Fourier transform. Tell me whether this transformation kernel is separable. Okay, I'm getting few answers. What about others? Please make an attempt. Is this separable? This DFT forward transformation kernel is okay. I got answers as not separable. Okay, now I got one answer which is correct by Sanidhya. Yes, Sanidhya, your answer is correct. This transformation kernel is separable. Why? Because we can easily write this e raised to minus j term into two components. I can write this as e raised to minus j 2 pi ux by m into another term e raised to minus j 2 pi vy by n. Okay. And you can associate 1 upon m with first term and 1 upon n with another term, right? So as we can separate this e raised to minus j theta term into two terms. So this first term we can call as G1 x comma u. Okay. And this second term we can call as G2 v comma y, right? So we can, as we can separate xu term from vy term, we can call that this, we can say that this DFT is separable. Two-dimensional DFT is separable because we can separate it into two terms, G1XU and G2VY. Okay. So this two-dimensional DFT is separable. Now tell me whether this transform is symmetric. Is it symmetric? Okay, so I'm getting wrong answers. This transform is separable as well as symmetric, because if you check the main functionality is e raised to minus j theta. Similarly, here for this second term, we have functionality e raised to minus j theta. Okay, so this forward transformation kernel of two-dimensional DFT is separable as well as symmetric. Okay. And this is very important property for two-dimensional transforms. Why it is important? Because of this separability and symmetry, we can easily compute this transform by applying one-dimensional transform twice. Okay. So we can consider the image as matrix. Okay. And this matrix has rows and columns. Okay. So because of separability and symmetry, we can first apply the transform, say row wise, then we get intermediate results. On these intermediate results, we can apply the transform column wise. Okay, so we can perform this two-dimensional transform operation simply in terms of matrix multiplications. Okay, and because of matrix multiplication, this implementation of two-dimensional transform becomes very simple. Okay, that's why this separability and symmetry property is very important. Because of separability and symmetry property, first we can apply the transform on rows, we will get partial result. On partial result, we can apply the transform column wise, and then we get the final result. Okay. Okay, so this is your forward transformation kernel for discrete Fourier transform. This is separable because we can separate these terms as e raised to minus j 2 pi ux by m and e raised to minus j 2 pi vy by n. And both of them have same functionality. That's why it is separable as well as symmetric. And because of separability and symmetricity, we can compute the transform in terms of simple matrix multiplication. Okay. So now, according to this functionality of G, X, Y, U, V, we can get various transforms. Okay. So for Fourier transform, we have this equation e raised to minus j theta. Similarly, for discrete cosine transform, we can have different type of forward transformation kernel. In case of Fourier transform, it is e raised to minus j theta term. So tell me whether this Fourier transform is real transform or complex transform. Please type your answer. Whether Fourier transform is real transform or complex transform. Yes, your answers are correct, Sai, Aryan, Mehak. It is complex transform because there is a term e raised to minus j theta. Okay, so e raised to minus j theta actually represents cos theta minus j sine theta. So there are terms which involve sine terms as well as cos term. And sine and cos are orthogonal to each other. They have 90-degree phase shift. Okay, so that's why this transform gives you complex numbers as coefficient values. So this Fourier transform is complex in nature. If we say discrete cosine transform, this discrete cosine transform only has cos terms, so it is real in nature. It doesn't have sine terms which are 90-degree out of phase with the cos terms. Okay, so that's why discrete cosine transform is real transform. So now when we vary this functionality g, x, y, u, v, we get different types of transforms. Okay, so we can have different types of transforms as shown here: discrete Fourier transform, cosine transform, Walsh transform, Hadamard transform, Haar transform, and Karhunen-Loew transform. Okay, so these are various transforms, and according to the transform, this forward transformation kernel GXYUV and inverse transformation kernel HXYUV is different. It is different for different transforms. Okay. Now, before going to details of this transform, we are going to have a look at what is meaning of filtering concept in frequency domain. Okay. So basically, we can enhance the image in frequency domain by using frequency domain filters. Okay. Now, when we want to perform filtering in frequency domain, these are the various steps. First, we multiply the input image by minus 1 raised to x plus y. Then we transform this image to frequency domain by using one of these transforms. Okay, for image enhancement operation, we usually use discrete Fourier transform. Okay, so we apply the transform on the image to get frequency domain of the image. Then in frequency domain, we multiply the image by filter function. We know that convolution in time domain is equivalent to multiplication in frequency domain. Similarly, two-dimensional convolution in image space is equivalent to multiplication in frequency domain. Okay, so we take frequency domain of the image by transform, by applying a transform. Then we simply multiply those values with desired filter function. Okay, so when we multiply it by filter function, we get enhanced image in the frequency domain. Then we apply inverse transform on the filtered image in order to get enhanced image in image plane. Okay, so we perform application of filter in frequency domain, that is multiplying transform with the filter function. Then we apply inverse transform to reconstruct the original image, and again we multiply it by minus 1 raised to x plus y. Okay, so these first three, these middle three steps are very important. First, transform the image to frequency domain, multiply it by filter function, and then take the inverse transform to display the enhanced image in original image domain or original image space. Okay, now why do we need these additional steps, multiplication by minus 1 raised to x plus y? Reason is here, in case of images, we use uh, leftmost topmost corner as origin 0, 0. Okay, so in case of images, we consider image as shown here. Here, this is your origin of image, which is 0, 0. Then along this x direction, we go on increasing column numbers, and along y direction, we go on increasing row numbers. Now, when we use filter functions, these filter functions are centered around origin. Okay, so for filter functions, origin is considered here, which is at the center of the image. Okay, so in or before applying the transform, we need to shift this origin from this location to center of the image, which is say n by 2, m by 2. If your image size is n by m. Okay. So in order to perform this operation, we need to multiply each pixel by minus 1 raised to x minus 1 raised to x plus y, because translation in frequency domain, this is translation from this position to this position, translation in frequency domain is equivalent to multiplication by minus 1 raised to x plus y in image space. That's why before applying transform, we multiply image by minus 1 raised to x plus y. Now, after this multiplication, we take transform of the image, then we multiply it by filter function, then we take inverse transform, and again, now when we want to display it as image, we need to adjust this origin to original position, that is this corner, topmost left corner, right? So that's why we again multiply it by minus 1 raised to x plus 1. Okay. But as far as filtering is considered, these middle three steps are very important. Okay. Okay, so how we can achieve this filtering in frequency domain? We simply multiply transform of the image by filter function. So here FUV is transform of the image FXY. HUV is nothing but filter function in frequency domain. Okay, so HUV is your filter function. And when we multiply transform of the image FUV, with filter function, we get enhanced image GUV, okay, or filtered image GUV. Now when we want to display it as an image, again we need to apply inverse transform of the on the image. So inverse of GUV gives us GXY, which is enhanced image or filtered image, okay. And according to desired enhancement operation, we need to select appropriate filter function. Okay. So we can have various types of filters, okay, according to the filter function, HUV. Okay. So like we studied image smoothing and sharpening filters, we can have similar filters in frequency domain. Okay. So we can have low pass filters for blurring the image, or for noise removal, we can use low pass filters. For sharpening purpose, we can use high pass filters. Okay. So according to the filter function, we can get various types of filters. Okay. So this multiplication in we can achieve filtering simply by this multiplication operation. GUV we can obtain by multiplication of filter function HUV and FUV. And this frequency domain multiplication is equivalent to convolution, two-dimensional convolution in spatial domain or image space or image plane. Okay. So this simple multiplication in frequency domain is equivalent to convolution operation in spatial domain. So we can represent this, its equivalent in spatial domain as GXY is equal to HXY convolved with Fxy. So here this star represents two-dimensional convolution operation. Okay. So we have already studied this two-dimensional convolution under image enhancement unit. So this two-dimensional convolution is equivalent to multiplication. Okay. So this HUV is our filter function, and HUV decides type of filter. Okay. So that's all for today.